Hello and welcome to your Week 9 video for NUC 110. This week we are going to review the RHR video and PowerPoint that we're making now. We're going to define some terms. We're going to draw and label RHR, and it's going to give you the different pieces and parts that you need to make sure you include in there, and then list all modes of the RHR system, and then tell me the purpose of each mode. So RHR, residual heat removal, that is our last ECCS system to cover, and the purpose of it is to remove stored and decayed heat from the reactor and from containment during normal shutdown and accident conditions. So that's a pretty big job. The main one that we've talked about before is LPC. So low pressure coolant injection. It's going to put water in the reactor if the reactor is at a low pressure and it's losing water for some other reason in an emergency. So that's job A1, but it has a ton of jobs. Look how broadly this is worded. Remove stored heat, remove decay heat from the reactor, from containment during normal shutdown and accident conditions. So there's a lot of wiggle room in there in this overall purpose. So here are some things that it can do. Remove decay heat from the reactor during shutdown. So the reactor shut down and there's a lot of heat in there. We can use this system to cool it off. It can cool the suppression pool or the torus. So if we dumped a bunch of steam into the suppression pool and we need to cool it off, this is the system that is going to cool it off. It can spray the dry well. It can spray the torus. If there's a lot of steam in either the dry well or the torus, we can spray a fine mist on there to try to condense some of that steam and get everything cooled off. It can cool the fuel pool. It can take water from the torus and get it out of there. If there's too much water in the torus because of an emergency or whatever else, we can take that water from the torus and send it off to rad waste. And it can also, in a real emergency, the end times, it can inject service water, which is salty Brunswick River, Cape Fear River water, into the reactor. So certainly, whenever we start putting this salt water in, our service water is what it actually means, but we're going to call it salt water. That's going to be a big problem. So here are the different modes, and basically this entire PowerPoint is going to break these modes down. LPC, shutdown cooling, dry well and torus spray, suppression pool cooling, RHR service water injection, and then fuel pool cooling assist, and discharging the water to rad waste. So here is the RHR system. I have two loops, the left and the right. On the left, you'll see everything is labeled alpha. On the right, everything is going to be labeled bravo. And you can see I actually have two pumps. On the alpha side, I have alpha and Charlie. On the bravo side, I have bravo and delta. So I've got 4 pumps altogether, 2 per loop. So the next thing after the pumps that you'll come to is a heat exchanger. So I can bypass this heat exchanger if I need to, or I can send the water through the heat exchanger to cool it off. So I've got 2 different options right there. And then as it comes up, you can see it can go to the torus. It can spray the torus. It can come in and go underneath the torus to cool it off. We can cross tie the alpha and the bravo side. So here's alpha. I can open this up and then my sides are crisscrossed. And remember, when this jumps over, this is not actually a junction. So what this little jump is telling me is that these lines don't actually interact in any way, right? Just on this drawing. So as we keep trucking up here, you can see I can go through the 17 and the 15, and I can go into the recirc loop, and that's going to actually spray onto the fuel. I can also spray onto the dry well up here. So tons and tons of different modes. There's different places I can get my suction as well. I can take water right here from the reactor. I can take water from the torus, and over here's my discharge to rad waste. Over here's a discharge to fuel pool cooling, and right here is an intake from fuel pool cooling. So the fuel pool is just where we're keeping all that old fuel. Right after an outage, that water is very warm because of all the fuel we just pulled out that's been in there for 6 years. So we might need some extra fuel pool cooling. So we can use this side over here, the Bravo side only, to help us with that. So here are some of the components, some suction strainers down there in the torus just to keep any plastic bags and earplugs and screwdrivers from getting into our RHR pumps. There's always going to be minimum flow protection on these systems. There's a heat exchanger, the bypass valve that we just talked about for the heat exchanger. We didn't see this one in the drawing, but there are RHR is cooled by service water, and we want to make sure that the service water is at a higher pressure than my RHR water so that I don't leak the reactor into the environment. So I'm just going to use these booster pumps to push that pressure up And we'll talk about that more when we get to that slide. Some injection valves. We saw the 15 and the 17 there. Spray and cooling valves. The keep fill. All the systems have a keep fill. And then the rooms have a little air conditioner on them. We talked about that a little bit with core spray. So those suction strainers are the 13 concentric discs, and we have a ton of area there, 529 feet squared. So some of you, if you have a small apartment, you might be just around this 600 foot squared mark. So that's how much space we're giving ourselves to pull this water in so that we don't have any clogging issues. Here's a picture of them, right? You can see all these discs running down through here, and it's going to be very, very hard to clog this whole thing up, especially since it's 529 square feet of suction area. So the pumps are just centrifugal pumps, which is the typical normal run-of-the-mill pump, and they just spin and push that pressure up. They can pump up to 10,000 gallons per minute if the reactor is at 20 pounds. There's Alpha and Charlie and Bravo and Delta are the two different groups, right? Division 1 and Division 2, two different pairs. They're going to have everything independent at that point. They can get power from different diesel generators and things like that. The seal cooler, everything, all the cooling is going to come from service water. And there's pressure switches in there to make sure that the reactor is depressurized before this system tries to put water in. So here, this is a very, very cramped room. As you can see here, the motor is the dark green, and then down here on the bottom is our light green pump, and there's a little coupler for the shaft that goes between the motor and the pump. So it's a very crowded space, and it's very radioactive just because of all the years of water running through there. And these are all getting their power from different sources, normally from the grid, but for each one has its own diesel generator. So those main diesel generators that are outside, one of them will power this, one of them will power this, and you can see they're all four different. So there's a heat exchanger there that can take up to 8,000 gallons per minute, and it's just going to take water from the service water and cool things off as necessary. So in an emergency, we aren't immediately worried about cooling. Right at the beginning of the emergency, we just want to make sure that there's water on the fuel, no matter what the temperature of that water is. But if we go into day 4, day 5 of our emergency, we all of a sudden need to be cooling things off, and we can turn this heat exchanger on to start doing that. So that's what the heat exchanger looks like, and you can see there's a high do not loiter sign here. So relatively high radiation levels because there's lots of little tubes in here, and that reactor water's been running through, and little bits and pieces of fissionable or reactor fuel have gotten stuck in here. So you have a reasonably high radiation area where you don't really want to go and stand. And that heat exchanger goes down through the ground. You can see some insulation here just to keep the heat and the cool in. So there's a bypass valve for these heat exchangers, and normally we're going to bypass them. In any kind of emergency, we want them to be bypassed. So we're far more worried about that. So we actually can't even open them for a few minutes if LIPSI is in. So if we have a low level 3, then it's not even going to let us open these interlocks until that low level 3 clears for 3 minutes. So long term, we're going to go through the heat exchanger, but those first few minutes, we don't care. Just put water in there. So the outboard injection valve is going to be normally opened and actually gets its power from the opposite unit. Just in case we're having real issues here, we want to make sure that we can open and close this valve. So we'll take our power from the opposite unit. And the 15 is normally closed, and again, coming from the opposite unit. So, for whatever reason, we've completely lost power on this side, we still have this system available to us with the valves powered from the opposite side. We can also go and human power the valves if they're on the outside, but if they're inside the dry well in an emergency, we will not be able to get to them without killing some people. So here is our containment spray, just some nozzles up here, and I can start blowing water out of there if I am having any kind of an issue. So there's another one of the nozzles. So the keep fill, we talked about this last time. It's supplied by demineralized water, and it's going to prevent water hammer by just keeping that piping full of water. It's also going to minimize the injection time because I don't have to push the air that was in the pipes out. I have water in there already. So as soon as I start to push, the water that's in the pipe is going to get pushed into the reactor without having to be an issue. And if we get to the end times with these emergency procedures, you see EP, it's an emergency. OP is operating procedure, which is good. EP is emergency procedure, which is bad. This keep fill can also go into the reactor. So it's a relatively small amount of water, but we're in emergency procedures now. We're going to put water in there any way that we can. There's room coolers. If these things run for a long time, the rooms are going to start to get hot. And, the famous band 98 Degrees, this one is an easy one to remember for anybody from the 90s. So if the room gets too hot, these things are going to kick on and it's going to keep the room cool. And it's the same system as the others where there's just some service water and we blow a fan over it. And you have to have these room coolers. So here are our different modes. We'll go through them one at a time now. So low pressure coolant injection. It's going to turn on by itself if we let our reactor get to low level 3, or if we get to the combination of high dry well pressure and low reactor pressure. It's just going to reflow the reactor if there's a large line break, or if we use ADS. So we need to depressurize the reactor, and this thing is going to flood that reactor right back out. If the core is at 2/3 of core height, so we've let all the water drain out that can, one RHR pump can keep us right there at that, at that 2/3 core height. So we need at least 2 pumps to actually flood the thing out, and we have 4 altogether, so we can probably manage to piece together 2. So here is going to here is going to be the mode. I'm going to take water from the torus. It's going to go through these pumps, and it's going to go up into the recirc lines and get pushed into the reactor. And same on the other side. So the 2 sides are functionally identical. There's a couple of little differences, but I'm mostly going to focus on one side at a time because the 2 sides do the same thing. So shutdown cooling. If I'm in an outage, I can take water from the reactor. I can send it through the pumps and through the heat exchangers, and then send it straight back into the reactor, and it'll keep us cool at 125 Fahrenheit because we don't want too much evaporation to be coming off the reactor, especially when people are working up above the reactor during an outage. So if we get this close to 212 degrees where it starts to get close to boiling at the room temperature or room pressure, atmospheric pressure, there we go, then we want to make sure that we keep this nice and cool so the water does not evaporate and potentially contaminate people. So it's going to take actually water from the recirc line, but really close to the reactor. So this is we're poking a hole in the reactor here. So we have to be really, really, really careful that we aren't screwing something up. There's actually interlocks to make sure that we don't open this valve. So if I open these valves, I cannot open this valve because that would create like a little siphon from the reactor up into the torus. So if these are open, these suction valves for the torus have to be closed. But we're going to take water from the reactor, run it through the pumps, through the heat exchanger, and then it can go up this way and go back into the reactor the same way that the Lipsy water got in, right, through recirc. So this system is using recirc for a lot of things because, again, we don't want to poke any extra holes in the reactor vessel. So containment spray, there we go, emergency operating procedure again. So for some reason we're spraying the containment, severe accident mitigating guidelines procedure. So, we're in the bad times now. For whatever reason, we want to spray the dry well or we want to spray the torus. So for the dry well, that would mean that there's a big leak in here that's causing steam to run out and heat the dry well up very fast. We want to spray the dry well. For the torus, it would mean that we're dumping something in here that's heating up, that's either boiling the water or the steam is coming in here on the top and we need to cool it off. So we're actually going to take water from the torus and through the pump. We can use the heat exchanger or not. We can choose, and then we just want to spray it on top of the torus, or we want to come up here and just spray it on top of the dry well. And we saw those little nozzles at the beginning that are going to spray the water out that are in either the torus or the dry well. And if for whatever reason, we're in severe accident mitigating guidelines, we need to spray one of these things, this is the system that is going to do it. So another mode, suppression pool cooling. So I need to cool the torus, cool the suppression pool. I can just take water from there, run it through the heat exchanger, and run it straight back into the torus. And it's actually, a law of the land that we can't go above 170 degrees Fahrenheit. So we don't want that water boiling either. And if it does start to boil, then all of the systems that would be taking water from here are instead going to be trying to take steam from here, and that is not going to work. And if it's at 170 and I start taking water and changing the pressure, I could accidentally boil it inside the pump. So you really want it to be well below 212, and we've decided that this is a good line, 170 degrees Fahrenheit. Take the water from the Taurus, go through our pumps. This is a cooling, so it's going to use the heat exchanger for sure. And it's going to go through here, come back down, and go through the Taurus. So this is also our test path when we're trying to make sure that LIPC is going to work. We'll just take that water from the Taurus, and in that case, we'll go through this upper valve and just go straight back into the Taurus, just basically stirring the Taurus up a little bit and making sure that everything is going to work. And then we would shut the system off, open up our 15 up here, and if our 15 opens, then we know that our system would work in an actual emergency. So here's the end times now. We have, RHR surface water is over here. That's what's cooling the heat exchanger. So instead of going to the heat exchanger, I'm just going to divert some, and you'll see this. This is a physical piece of pipe that is missing because we never want somebody to accidentally inject salt water into the reactor. So we've actually taken a piece of pipe out of this just to make sure that it can never, ever, ever happen in a million years on accident. It has to be something where somebody put this piece of pipe back in there and bolted it on for us to be able to push this service water in. Notice that it doesn't use these pumps. It doesn't use the heat exchanger. We're just stealing some service water from there and dumping it into the reactor. We're having a really bad day at that point. This is the other side. So we're taking service water from outside from the Cape Fear River, and it's getting pushed up in here. And here are those service water booster pumps for the RHR system that are pushing the pressure up. And we're just pushing that pressure up because everything wants to go from high pressure to low pressure. So when it goes through this heat exchanger, we want the higher pressure to be the salt water. So we would rather have salt water leaking into the reactor than having the reactor leak into the salt water, because that salt water is going to eventually get discharged. So that would be an issue for the public, right? So if the salt water is leaking into the heat exchanger, that really sucks, and we're going to have to do something about it. If the reactor is leaking into the salt water and that's going to the public, well, now we have a huge nightmare, right? We're potentially taking fuel from the reactor and dumping it out there in the ocean for the public to swim around in. So these pumps have a very, very minute little purpose, right? Their whole purpose is to just increase that pressure so that the saltwater side is higher pressure than the reactor water side inside this heat exchanger. So fuel pool cooling assist right after an outage. We want to keep that fuel pool nice and close, cold, 125 Fahrenheit. Seems pretty hot, but again, this is going to be, the fuel pool is at atmospheric pressure. It doesn't matter if we're in an outage or not. You can do it during an outage with the gates removed, or the gate that's in between the reactor and the fuel pool can be installed so that they're two different tanks. Either way, we can try to cool this off, and we'll just take a little bit of water from the fuel pool cooling system and run it through our heat exchangers, and then run it back through the fuel pool cooling system. Or we can just take water straight from the reactor and cool it off through the heat exchanger and send it straight back into the reactor. So there it is with the gates installed. We're taking it from fuel pool cooling, sending it through here, and sending it back up to the fuel pool cooling system. So if the Taurus gets too full, I'm going to open some valves up, turn some pumps on, and I'm just going to take this water from the Taurus and send it to rad waste. So what is rad waste? It sounds like a terrible place. That is where all of our radioactive water, radioactive resin, all that other stuff goes there just to cool off for a while. And in the case of water, we're going to reprocess it and reuse it. We don't take in new water all the time. We will take in some, but we try to reprocess as much as we can, and we don't discharge any water if we can keep from it. Very, very rare for us to discharge water, less than once a year for any large amount. So we reprocess it and push it back into the CST, and the CST eventually rotates it back into the reactor. And when it leaks again, or when the Taurus fills up too much, we'll repeat the process again. We'll send it off to rad waste and clean it up. So we're taking it from the Taurus just through the pumps. We don't need the heat exchanger for this, and through rad waste, where we will reprocess the water. So any pump that we start up, we want to start it up nice and gently with some minimum flow action. And we want to wait about 10 seconds in the case of these to make sure that we have a nice flow and issues aren't occurring. So don't drain the reactor. We talked about that. There's lots of interlocks in there to make sure that you don't open two valves at the same time and end up draining the reactor. So all those interlocks and logic, you don't need to know each one, but you need to know the idea. Like if there's a potential for me to drain the reactor, you can bet that there's going to be a computer in there that's not going to let me drain the reactor. So how does this work with other systems? So fuel pool cooling, we just saw that. There's a way for us to grab some fuel pool cooling water, send it through our big RHR heat exchangers and cool everything off and then send it back to the fuel pool cooling. Service water is what's cooling everything. And we have those RHR service water pumps just to push the pressure up. And if we absolutely have to, we can push that service water into the reactor. Demineralized water is what's keeping everything full. Rad waste is where we're going to send any extra water that we have from the Taurus. And when at the end of an outage, we flood everything up during an outage. At the end of the outage, I have all that extra water in there that I need to drain. I'm going to take it from the reactor and send it to rad waste. So here is the big drawing, and again over here on the bottom are all my modes, right? It looks like there's 6 modes here altogether, but a couple of them are combined. And then over here is all the interlocks. You do not need to memorize the interlocks, but the basic idea is if I can drain the reactor on accident, the engineers that made this system are going to make sure that I cannot accidentally do it. So there's a couple of questions for you to answer. Please let me know if you have any you would like me to answer, and I hope you have a good week.